Do you recognize that number? You really should. The last time you were looking at a liter of a strong hydrofluoric acid and you're counting the number of hydrogen ions inside that liter of hydrofluoric acid, that's the number you should have counted. Well, that seems like a pretty large number. Let's say I asked you to stay after school at the end of the year to help me stack advanced functions textbooks. And I asked you to just make one big stack from the Earth all the way to the sun, and I would pay you $1 for that. Well, if this is the number of textbooks you had, then you could actually make more than one stack. If you made a second stack, well, then you would make $2. If you made a third stack, you could make $3. Well, if you stacked all of these books in stacks the size of from the Earth to the sun, you could actually make $200 trillion from me, because you'd have enough books to make 200 trillion stacks from the Earth all the way to the sun. That's a lot. Well, this super large number that you see here is called 1 mole. You probably learned that from chemistry class. So instead of writing these large numbers all the time, I'm going to do it in moles. So 1 mole of hydrogen ions per liter has a pH of 0. Now we have another acid, a hydrochloric acid, that's in our stomach lining, and it's a very strong acid, but it's only 1/10 the strength of the hydrofluoric acid you see. So that means it only has 1/10 of the hydrogen ions per liter. We say that that has a pH of 1. And since it only has 1/10 of the hydrogen ions, we say it has 0.1 moles of hydrogen ions. So 1/10 is 0.1. Lemon juice is about 1/10 as strong as your stomach acids, which also means that it's only 1/100th as strong as your hydrofluoric acid. So they say this has a pH of 2. So if you have something that has a pH of 2, you'd have to multiply the number of moles by 10 to the power of 2, or 100, to get something with a solution of pH with a pH of 0. Every time you multiply by 10 to the power of 1, or just by 10, you're going to get a pH of 1 less. I think it would be a cool challenge to ask you guys to try to find a formula for pH based on the number of moles of hydrogen ions in a liter of solution. Pause the video, see if you can come up with it, spend maybe 30 seconds to a minute on it, and come back. Alright, this is probably a tricky one, but if you just took the log with the base 10 of the number of moles of hydrogen ions in a liter of solution, that will give you the negative of the pH. So if you take the negative log base 10 of that, it will give you the pH. For example, if you have just 1 mole of hydrogen ions, well, 10 to the power of what gives you 1? Well, that's 10 to the power of 0. So the log of 1 base 10 is 0, pH of 0. But if you have 0.1 moles of hydrogen ions in a liter, well, then you have to put your H plus as 0.1. Well, the log of 0.1 base 10 is negative 1. Right? So it has a pH of positive 1 because it's the negative. So basically they could have done 0, negative 1, negative 2, negative 3 as the pH, but I guess scientists decided they don't want to work with negative numbers. Now, they didn't really avoid it. No, they mostly avoided it, but if you get a really strong acid, you could actually pump in more than a mole of hydrogen ions into a solution. If you did 10 moles of hydrogen ions into a liter of solution, well then yeah, you'd have a pH of negative 1. Because 10, the log of 10 base 10 is equal to 1, and then it would be the negative of that, negative 1. So you could actually go into the negatives for pH. That would be very acidic. Pure water is not an acid at all. Once you get below 0.000001 moles of hydrogen ions per liter of solution, it's no longer an acid. So pure water is neutral. Can you either guess or figure out the pH of pure water? Pause the video, take 10 seconds, see if you can get it. Well, the number of hydrogen ions is only 1/100,000th of the number of hydrogen ions in lemon juice. So you'd have to multiply by 10 to the negative 5 to get from the number of moles in lemon juice to the number of moles in water, which means the pH is going to increase by 5. So water has a pH, pure water has a pH value of 7. We could also have used the hydrofluoric acid as an example. There's 1 mole of hydrogen ions per liter there, and you have to divide by 10 million for the number of moles of hydrogen ions in pure water, or dividing by 10 million, you could say it's times 10 to the power of -7, and so the pH is going to go up by +7. Let's try the actual equation. Let's plug in 0.000001 for our H plus and take the log of that base 10, take the negative of that, and you get a pH of 7. Log of the base 10 of this number is -7 because 10 to the -7 equals 0.000001. And then if you take the negative of -7, you end up with a pH of 7. Well, what about baking soda? Now you have even less of a concentration of hydrogen ions, and it's not an acid. Now we're talking about an alkali, or a base, which has the opposite properties of an acid. Baking soda is 1/100th as strong as water. So tell me, what is that pH? Pause the video, tell me what the pH is this time, and then come back to me. There are a few ways to solve this. You could just simply plug in 0.000000001 in for H plus in the equation. So pH equals the negative log of that, base 10, and you get an answer of 9. A few other ways of doing it. You could see that you just have 2 extra zeros from the water solution, from the pure water solution, and so you know that to get from the number of moles in water to the number of moles in hydrogen ions, you just have to divide by 100 or multiply by 10 to the power of -2, so your pH should be 2 greater. If you've taken care of a pool before, you might know that you would like to have a pH value of about 7.4. That's because the tears in your eyes have a pH value of about 7.4, and you want to match the pH value of the water to your teardrops. That way when you go in underwater, your eyes don't really feel soreness because they're used to the pH level. Now my question to you is, how much stronger is pure water to pool water with a pH of 7.4? We're assuming that the hydrogen ion concentration is the measure of the strength. So how much stronger would lemon juice be than pool water as well? Remembering that pool water has a pH of 7.4 and lemon juice has a pH of 2. As always, pause the video, take your pencil and paper out, try to get the answer, and come back. Well, we know that the pH of pure water is 7 and the pH of pool water is 7.4. And so the concentration of hydrogen ions in pool water has to be multiplied by 10 to the power of 0.4 to get the concentration of hydrogen ions in pure water. So 10 to the power of 0.4 is equal to approximately 2.512. So that means that pure water actually has a hydrogen ions concentration about 2.5 times that of pool water. Similarly, lemon juice is 5.4 less on the pH scale. So that means to get from the concentration in pool water to the concentration in lemon juice, you have to multiply by 10 to the power of 5.4. 10 to the power of 5.4 is about 251,188.6. You may have noticed that lemon juice has a pH value that's 5 less than pure water, which means it's actually 100,000 times stronger than pure water. So you could have just multiplied our original answer by 100,000 and gotten the same results. Now you might be wondering, why do they use this log scale to talk about pH? Why don't they just use a linear scale like we usually use? So here's a graph of different solutions and their hydrogen ion concentration. As you can see over here to the right, we have battery acid or strong hydrofluoric acid. We talked about that before. And this has 1 mole of hydrogen ions in 1 liter of the solution. Right? So we've got that right here at 1. The next highest we have here is your hydrochloric acid that we talked about, and that's at 0.1 moles per liter. And so that goes right there. The next one is going to be lemon juice at 0.01. Well, that's 1/10 of the way there. And then you got your grapefruit juice at 0.001 right there. You got tomato juice 0.0001. And if you can see, all these soft drinking water, urine, seawater, all these different things, all are squeezed into here. Now remember, each one is 1/10 of the one before. But this isn't a very good graph, is it? All right, so you think, okay, well, maybe a solution is to just cut out this battery acid. That's the culprit here, right? And we'll stretch it out, and maybe we'll just get, we'll just go up to 0.1 so that we can see only the guys over here. Or even, you know what, maybe we'll make it even better. We'll go twice. We'll squeeze it in. We'll just get all these little ones here. So let's see what happens when we do that. First, I'm going to cut it down to just over 0.1, and then I'm going to cut it down to 0.01 just to see what happens. All right, this is zoomed in by a factor of 1/10, so we're right in close here. And off to the right, now you can see hydrochloric acid that used to be right in here is now stretched way out to here, which is good. Now we can see a nice distance between them, right? The battery acid, no, that's off the screen. That's like 10 screen lengths way to the right now because we've really zoomed in tight here. Now the lemon juice that used to be in this chunk has now come out nicely. We can see it. Grapefruit juice, well, that's in with the chunk, and then everything else is all in this little area. All right, well, let's zoom in even farther, see what happens. Okay, now we're really zoomed in. Like this is at 0.01. That's like, back then that was like just this little area before. We've zoomed that way out to here. Now your battery acid, well, that's 100 screen lengths this way, so it's way, way, way to the right. This hydrochloric acid in your stomach lining, that one that we talked about, well, that's now 10 screens over, right? So that's the one that used to be here. After one zoom in, it went to here, and now it's way over. So now we're trying to graph all these things. Now we've completely lost these two. And the rest, well, it's no better. Now we got our lemon juice that's out here, and grapefruit, yeah, we can see that, but then everything else is bunched again. Every time you zoom out, you're going to have the same problem because these are not really close to each other like it seems. Each one is 10 times the distance than the next, right? So you have like 1/10 and then 100th and then 1,000th all the way through. So if you just have a normal scale that we're used to seeing, a linear scale, it's not going to work for this sort of thing. Now let's do a logarithmic scale. Now whoever developed the pH system also provided an equation so you can easily convert, but these numbers are much nicer here. So once you convert using this equation and find the pH instead of just finding the ion concentration, now look at this graph. You've got your battery acid. That's now this one's, notice that the stronger stuff is to the left and the weaker stuff is to the right, and that's because we're doing the negative log. So normally it would be the opposite, but they took the negative log just to keep the numbers positive. So battery acid you have right here, and then you've got your hydrochloric acid and your lemon juice, your grapefruit, and everything is nice in line and evenly spaced out here, and you can see everything. So obviously that's an excellent solution to a linear graph where you're either going to see, you only get to see about 3 things at a time no matter how you zoom in or zoom out. Keep in mind when you read this scale, you have to think it through. So if you take, let's say, baking soda for example, seawater is 10 times stronger than baking soda, even though it's only 1 tick to the left. And pure water is 10 times stronger than seawater. And so pure water is actually 100 times stronger than baking soda. It's 2 ticks to the left, which means it's 10 to the power of 2 stronger concentration, right? So if you do let's say 2.4 ticks to the left, well then this value on the left is 10 to the power of 2.4 stronger of a solution than here. And to go to the right, you would just have to multiply by 10 to the power of negative 2.4. We've kind of run into the same problem with earthquake intensities. So after scientists have measured the intensity of earthquakes, it is nearly impossible to put it on a linear graph just because of the nature of like how some earthquakes were just so much more intense than others. And when you put that really, really intense one onto the scale, well, then the others all get squished into a little area, so it's hard to put everything on this scale. But the solution, again, is a logarithmic scale. So just like what we did with pH values and solutions, we could put the magnitude of earthquakes on a logarithmic scale. Notice there will be a little bit of a difference between pH and earthquakes in that the intensity of earthquakes, the more intense earthquakes are to the right, whereas for pH, the more intense acids were to the left. And that's because for the pH, we took the negative log, and for earthquakes, we just take the normal log. Now, you've all probably heard about the Richter scale. Well, what we're using here is the moment magnitude scale. It's actually the scale that you'd see more commonly used these days. It's very close to the Richter scale. Most earthquakes have about the same value anyway. It's just the more intense earthquakes that have, it's kind of like it distinguishes one from the other a little bit better, they say. And so that's what we use. But it's pretty close to the same idea as the Richter scale. And I'm pretty sure everyone just calls it a Richter scale anyway. So if you look here, we have a logarithmic scale. I've got it from 0 to 10. This year alone, there were over 5,000 recorded earthquakes with a magnitude between 4 and 5. There were another 613 earthquakes that had a magnitude between 5 and 6. Now, if an earthquake has a magnitude of 5 and another earthquake has a magnitude of 6, how much more intense is the earthquake of magnitude 6 than that of magnitude 5? Pause the video, see if you can answer that question, and come back. Well, hopefully you answered about 10 times as big. This is a logarithmic scale, so that means every 1 to the right is 10 to the power of 1 more intense. Now, if you got it wrong, I'd have to forgive you because I never actually told you the base of the logarithm was base 10. But I think that's just commonly, because we count in base 10, I think most scientists would opt for a base 10 logarithm when they use one. All right, let's quickly check your understanding. The most intense Canadian earthquake this year happened on May 22nd, and that had a magnitude of 4.9. In 1949, there was an earthquake. It's considered the second largest recorded in Canada. That had a magnitude of 8.1. How much more intense was the 1949 earthquake than the 2020 earthquake? Of course, pause the video, do the work, and come back. All right, since the 1949 earthquake had a moment magnitude of 8.1 and the 2020 had a moment magnitude of 4.9, 8.1 is 3.2 larger. That means that the intensity of the earthquake was 10 to the power of 3.2 times the intensity of the smaller one. 10 to the power of 3.2 is approximately 1,584.9. So that means the one in 1949 was 1,500 or 1,600 times the intensity of the greatest one this year. Another worthwhile logarithmic scale to talk about is decibels. Decibels measures the intensity of sound, and the loudest sound that we can hear is about 10 trillion times as loud as the quietest. So again, a logarithmic scale is appropriate. Now this system is built so that the quietest sound we can hear is 0 decibels, and we use this equation here to calculate the loudness in decibels, where x represents how many times the intensity of sound is compared to the quietest sound we can hear. So if something is twice as loud as the quietest sound we can hear, then its x value is 2. If it's 100 times more intense than the quietest sound we can hear, then its x value is 100. Now be careful with this equation. Like with the pH, we had a negative in front of the log, which reversed directions of the scale. It made the most intense acids to the left and the least intense solutions to the right. Well, here we don't have a negative, but we do have the number 10. And what that does is it makes the decibels 10 times greater. So instead of a decibel difference of about 1.7 giving us an intensity ratio of 10 to the power of 1.7, it actually takes a decibel difference of about 17 to get an intensity ratio of 10 to the power of 1.7. So when you want to know how much more intense one sound is than the other, you can take the decibel difference, but then you have to divide by 10 before you do 10 to the power of that. So I have no idea why they decided to put a 10 here. I guess they'd like the decibels to go 0, 10, 20, 30, 40, 50, 60, 70, 80 instead of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe it's nicer for people to see less decimals when they're talking about different things with different decibels. Either way, you have to consider that when you're trying to find out how much one sound is more intense than the other. So a sound that's 70 decibels is 10 to the power of 1 times more intense than something that's 60 decibels. Instead of 10 to the power of 10, it's 10 to the power of 1. All right, for your last challenge of the day. So in 1972, Deep Purple, which is a band, set a world record for the loudest concert at 117 decibels. From my research, the Sacramento Kings actually had a game where they hit 130 decibels in their stadium. Now, how many times the intensity of that rock concert that set the world record was this arena in Sacramento? For the last time, pause the video, come back when you think you have the right answer. Now we know the equation for loudness in terms of intensity. So we start off with the loudness of the basketball arena. We already know the loudness of the basketball arena is 130 decibels. And so let's solve for x to see the intensity. Right, so 130 equals 10 times the log base 10 of x, so we divide both sides by 10, you get 13 equals the log base 10 of x, and then you transfer that from a logarithm to an exponential. So you have 10 to the power of 13 equals x. There we go. Now do the same thing for rock concert. We know that the rock concert was 117 decibels, and so let's solve for x. 11.7 because we divide by 10, and we change it to an exponential. 10 to the power of 11.7 is equal to x. And we want to know the ratio of how loud the basketball arena was compared to the rock concert. And so that's just 10 to the power of 13 divided by 10 to the power of 11.7, which is 10 to the power of 1.3, or approximately 20. So the basketball arena was actually about 20 times more intense than the rock concert. Now, if you're clever, you might have just noticed that the basketball arena was 130 decibels and the rock concert was 117 decibels. And 130 is just 13 more than 117. So if you subtract 130 minus 117, you get 13. And so divide that 13 by 10, and you get 1.3, and 10 to the power of 1.3 is about 20. Now I think you'll find that logarithmic scales are quite popular. As you go through life, you'll find more and more situations where logarithmic scales are either necessary or convenient. One that I thought was kind of interesting, you might want to take a look at. Go look up the distance to the sun of each planet in our solar system. It's kind of interesting how far they are from the sun, and look at it from a linear standpoint and look at it from a logarithmic standpoint, and I think you'll find something very interesting.